far as chemistry is concerned. So we are quickly going to run through chemical equation. Okay, so right before this class, I'm sure you must have been writing some chemical equations, balancing of equations, and all of that. But do we actually know the basis of what we are doing? So in this lecture, we're going to see how we can balance chemical equations, types of equations, and many more as well. So here's um so also we are going to look at shorthand representation of a chemical change with symbols and formulas. Or let me just say that chemical equations can be representation of a chemical change with symbols and formulas. So talking about symbols, you have to know the uh, symbolic representation of elements, and also you have to know formulas when elements are combined together to form compounds, molecules, ions, or radicals. So they are important. So all of those we're going to apply in chemical equation. So let's quickly look at a word equation. Can you hear me?
Yes, sir.
Okay. Let's look at a word equation where we have sodium combining with water, leading to the production or formation of sodium hydroxide and hydrogen. So to represent that using chemical formulas, that is the shorthand representation, you're going to have it in that format. We have sodium combining with H2O. Yes, it is important that you must know what is the chemical symbol for sodium. That is Na. That's from natrium. Natrium. Natrium as Na, sodium. And water, you must know the chemical formula for that, which is formed from the combination of hydrogen and oxygen in the ratio 2:1. So when the two of them combine together, it results in the formation of sodium hydroxide, which is NaOH. Important to know that as well. And then hydrogen. So for you to balance an equation, you must be able to interpret, or you must be able to present this word equation into the chemical equation. Okay, sodium, this is sodium. Water, this is water. Sodium hydroxide, this is sodium hydroxide down here. Hydrogen, this is down here. You must know that hydrogen does not exist just as ordinary H. It must have subscript 2. Like these two at this lower level here, which indicates that hydrogen is a gas. You can't have hydrogen standing alone. Hydrogen will probably, when you're going to have it in this state is when it's combined with other elements, as you can see here in sodium hydroxide. And actually, it's not standing alone. It's a combination with other elements forming another compound entirely, sodium hydroxide. Okay. Does it make sense? Hello, can we hear me? Have I?
Yes, sir. Yes, sir.
Okay. Why do we have just three people on this session? Uh, Nima has gone again. Okay, let me try to communicate with them. If Captain, I think we forgot about attendances. You've not been taking attendances anymore, right? Imagine.
No, I should take it.
Okay, very good. All of them missing session like this. No, imagine. There are quite a lot of people not on this session. It's okay. Oh, that means I will continue. Okay, so let's continue. So result to we have combination of sodium with hydrogen water, so sodium hydroxide and hydrogen gas. So all what you have on this left hand side to be considered as the reactant, and all what you have on this right hand side are meant to be considered as the product. Okay, so again, this is the equation: sodium combining with water, H2O. You have it resulting to the formation of sodium hydroxide and hydrogen gas. So what are the informations you can get from this chemical equation? Number one, it shows correct symbols and correct formulas of the substances. So when you are given in words, you must be able to tell us what's the correct symbol for sodium, which is Na. You must be able to give us the chemical formula for water, which is H2O, which is a substance here. When you hear sodium hydroxide, you should know that sodium hydroxide is Na.
I can't see your screen.
Can anybody see my screen? Animation, can you see the screen?
Yes, sir.
Okay. Smadia, you should check your network again.
I can see it now.
Okay, that's very good. So, what are the information we can get from this chemical equation? It shows, or chemical equation shows correct symbols and correct formulas of the substances. This is for sodium, this is for water, H2O, this is for sodium hydroxide, NaOH, and this is for hydrogen gas. Okay. Number two, it shows the arrangement of atoms. Yes, you can see when you have combination of this with this, there is rearrangement. Oxygen goes to combine with sodium and then leaving hydrogen remaining, one hydrogen there, which is what you're having here. And then at the same time you have H2 standing alone here. So there's a kind of rearrangement going on there of atoms. Also, it shows the smallest whole number ratio of atoms. So yes, it also shows whole number ratio of atoms. So here you have just one uh, what's it called now? This tells you that from this equation here, you can easily say, maybe suppose you balanced this equation now. As we're having it here, it's not actually balanced like this, because yes, you have one sodium here, you have one sodium here, you have two hydrogen here, you're having one hydrogen here and then two hydrogen. That is three hydrogen here. You have one oxygen and here, you have one oxygen here. It implies that the equation is not balanced in terms of the number of hydrogen. There are three hydrogen on the product side, and there's just two hydrogen on the reactant side. So suppose we balanced it now. Let's say if you are to balance this equation now, uh, it requires putting some certain numbers beside those reactants and then the product, so that you can derive that okay, a certain number of this is reacting with a certain number of this to give a certain number of this and a certain number of this. From this equation now, although it is unbalanced, I can say that 1 mole of sodium, or one sodium, is combining with one water to give one sodium hydroxide and one hydrogen gas. So that is unbalanced. So when we balance it, of course, we expect that combination ratio to change. So let's see as we progress. So it also shows the mass relationships of the substances. Yes, we are going to see that as we progress. Okay, let me let's write some equation here so that we can better understand what I'm trying to say there. Okay. Okay. Let's use this one. Can we still hear me?
Sir.
Oh, okay. Aliyah, where were you? Oh, is that not Aliyah? Oh, maybe she's not the one.
No, sir.
Is that not Aliyah?
No, sir.
Oh, okay. Oh, is that Kodija?
Yes, sir.
Okay. So imagine you have this equation here. You have sodium combining with water. I'm trying to write that equation out. to give NaOH plus H2. Now we all know that this equation is not balanced, right? So to appreciate the number of ratios of each of those reactants or products that are reacting together, there is one sodium, one sodium. It has just been denoted that you have 3 hydrogen on this side, and then you have 2 hydrogen on this side. So to balance it, this is 2 here, right? You already have 2 here, but there is one hydrogen moving along with this one here, right? Although when you want to balance a chemical equation, you could also use fractions to balance an equation. Okay, you have 2 on this side. There is 1 on this side, but there's 2 on this side. I can simply balance that 2 by putting a half there. When I put a half there, it returns this hydrogen, these 2 hydrogen that you're seeing, it breaks it down to 1. So that 1 plus 1 can make it equal to the 2 that you are having on this side. This is now 1 hydrogen on this side. This one is also 1 hydrogen on this side as well. So that 1 plus 1 can be equals to 2 hydrogen. Are we together? Are we still together?
Yes, sir.
Okay. But usually you don't leave this half hanging there. You usually want to multiply all through by this denominator value, by this 2. So when you multiply everything all through by 2, let me say this is the equation, right? You multiply it by 2 by factor 2. When you multiply it by 2, you are basically going to have, oh sorry, okay, we are going to have 2Na plus 2H2O to give 2 NaOH plus H2. Now in this case, the equation is balanced. Now, when the equation is balanced, you are then able to say, you're able to give the relationships of the atoms or molecules and how they are combining. That 2 moles of this is reacting with 2 moles of this one to give 2 moles of this to 1 of this guy. So that is what that statement here was trying to tell you, that it shows the smallest whole number ratio of atoms. So here 2 of sodium is reacting with 2 of this water molecule that I see here to give 2 of this sodium hydroxide and 1 of this hydrogen here. So as they are as the equation is balanced here now, you can also bring out a mass to mass relationships. What is the mass to mass relationship you can bring out here? It implies that you are relating their molar masses. Molar mass of sodium is molar mass of sodium is what? Who can tell me? Can we hear me?
Yes, sir. 23.
Ah, okay, 23. I don't know why the board is doing that way. Okay, the molar mass of this sodium, that is 23 grams. Water is what? 18 grams. Sodium hydroxide is what? 40 grams.
Come.
And then hydrogen gas is what? 2 grams. So
Sugar.
from here now, if you want to relate their masses together, that's mass to mass relationship. you can easily say that 2 times 23 gram of sodium to the ratio of 2 times 18 grams of water is 2 times 40 grams of sodium hydroxide to animation with yourself 1 times 2 gram of hydrogen gas. Does it make sense? Does it make sense?
Yes, sir.
Okay. So show the mass relationship of the substances. We've discussed that. Now let's look at some symbols where it is placed and the meaning. So wherever you see S, like X within a bracket here, it's usually after the substance and it indicates that the substance is a solid. Substance is a solid. If you see gas like this, it's also after a substance, it's a gas. That's talking about the state of matter of the substances now. Where you see L is also indicate that the substance is a liquid, and um, when you see this arrow going up beside a particular substance, it indicates that there is evolution of a gas. That is, the gas is giving off. And then when you see a down arrow after the substance, it indicates that there is formation of a precipitate. And then when you see AQ, that's also after the substance, indicate that it is dissolved in water. That is aqueous solution. Okay. So when you see this one, it indicates that you usually have it between placed between the reactants and the product. So indicate that the reaction is a reversible reaction. It is reversible. Where you see equals sign, uh, is usually placed between reactants and products and indicates that the reaction has attained equilibrium. Okay, equilibrium. And then when you see something like this, also placed between reactants and products, usually on the single arrow, it indicates that it is needed for the reaction to come to complete. Does that make sense?
Yes, yes, sir.
Is it only animal sound that we have in this class?
Yes, sir.
So someone should screenshot this and send to the platform. So if you've done so, let me know, please.
I've done it, sir.
Okay. So classifying chemical equations, very important. Chemical equations, you could classify them into 4 major categories. Combination reactions or let me say combination reactions leading to combination chemical equation. You could have decomposition. You could have a chemical equation that involves single substitution, or you could have a chemical equation that involves double decomposition. So taking each of them one by one. When we're talking about combination, a combination reaction. So this is the form of equation you are going to see there. You have a reactant A combining with reactant B, and the result to the formation of product C. So there is usually the formation of a single product, A plus B giving C. So you have element 1, another element, and then you have the result of a binary compound. So for example, when you have sodium combining with chlorine, this chlorine gas here. So what do you think I'm going to put here? Anybody? What do you think I'm going to put at the subscript level just beside this sodium here? What am I going to put here? We've just done that on the table. I said you should screenshot. What are we going to put here? Nobody is saying anything. What are we going to put here? What's the state? Or what will be the state?
Solid.
So yeah, you're going to have solid here in your bracket. F.
Solid.
You're going to have your bracket here. G, gas. The gas. and then it results in formation of a solid as well. S will be just right here, sodium chloride. So also in a combination reaction, you have this hydrogen gas result combining with oxygen gas, results in formation of water, H2O. So this is also a combination reaction. And at the same time, it could be called combustion reaction as well. Could be called combination, could be called combustion. Combustion, why? Because there is oxygen involved here. You can simply say that hydrogen is burning in oxygen, okay? Hydrogen is burning in oxygen, so resulting to the formation of H2O. So balancing of this one, remember I mentioned that you can put half. In a case whereby you have a substance standing alone, and then you are having unequal number, just take the fraction. So take the fraction to balance it off with what you are having on the product side. Here you are having just one chlorine. Here I'm having two. Just take the fraction 1/2. Here I'm having one oxygen. Here I'm having to take the fraction 1/2, and then you multiply through by 2. When you multiply this one through by 2, you're going to have 2Na plus Cl2 equals 2NaCl. When you multiply this all through by 2 as well, you're going to have 2H2 plus O2 to give you 2H2O. In that case, it is a balanced chemical equation. Does it make sense?
Yes, sir.
Yes, sir.
So
Yes, sir.
what you're trying to say there, okay, sorry, you have Na plus Cl2 to give NaCl. Talking about the states now, this is a solid, this a gas, and this one is a solid, right? Now this one is 2 here, but what you are having here for chlorine is just 1. So to make it equal, you take the fraction of the value of what you are having here. If you're having, suppose you're having Cl3 here, that means you are going to take 1/3. Anyways, the Cl3 doesn't exist. I'm just saying, just using that to explain. So multiply all through by 2. Multiply the whole of the equation by 2. When you multiply the whole of the equation by 2, then you can have 2Na solid plus the 2 is going to cancel out this half, because you're going to have 2 times 1/2 Cl2. So this is going to cancel out this. So you have resulting to the formation of 2NaCl solid. Eventually, all balance to be 2Na solid plus Cl2 gas, resulting to the formation of 2NaCl solid. Okay, so continuing from where we stopped in the presentation, so same thing for water as well. We do that for water, you're simply going to get the same thing. It's the same approach. Now when you have compound plus compound combining together, you have a tertiary compound, so it is also a combination reaction. So for example, you have a metallic oxide combining with water, the result to a base. Now this is a metallic oxide here, that's magnesium oxide, and then combining with water resulting to the formation of magnesium hydroxide, MgOH2. It's also a combination reaction, which I'm pretty sure you can balance this. Can we? Is it balanced already? Can anybody tell me?
Yes, sir. Yes, sir.
Okay,
Yes, sir.
okay, it's balanced. Okay, yes, it's balanced. Next one, you have non-metallic oxide with water to give an acid, CO2 combined with H2O to give H2CO3. It's also a balanced equation already. Also, you have metallic oxide with non-metallic oxide to give salts. All of these are combination reaction. You have just a formation of a single product there. So this one, calcium oxide reacting with CO2, resulting to the formation of calcium tribicarbonate 4 calculate. So it's also a combination reaction. So now decomposition. You have a single reactant here, and then it dissociates, or let me say kind of it divides. Or let's use decompose. So you decompose and then you have formation of two products. So C gives A plus B. C gives A plus B. So for example, KCl decomposes to give potassium and then evolution of a gas. So you're going to have an arrow that points upwards here, showing that there's evolution of a gas. Okay. Also, you have aluminium hydroxide. So aluminium hydroxide is also going to dissociate, or let me say decompose. When it decomposes, it results in formation of bauxite. That's Al2O3, aluminium oxide. Yes, aluminium oxide, Al2O3, and also formation of H2O. We get to understand bauxite very well when we get to metal and its compounds, where we talk about each of the metals. So that's also a decomposition reaction there, okay? And then single substitution, you have just one single substitute that you're having this C now replacing this A here, resulting in formation of CB, and then the A goes there to stand alone, whereby this C is a metal or a more electropositive component. Because anything that can displace this A from here means that that C must be more electropositive than this A. Okay. So usually metals are more like metals that are more electropositive are able to displace those that are less electropositive. So as you can see here, C is greater than A. That's the metallic activity. That's the activity series or electrochemical series. So and that's because it's able to lose its own electron faster. C is able to lose its own electron faster. That's what we call electropositive. Okay. So and this is the activity series as we've done before when we're dealing with electrolysis. So potassium is greater than barium, greater than calcium, greater than sodium, greater than magnesium, greater than aluminium, greater than zinc, greater than chromium, greater than iron, greater than nickel. Also greater than tin, greater than lead, greater than hydrogen. So you have hydrogen here, greater than copper, greater than bismuth, greater than mercury, greater than silver, greater than platinum, and then greater than gold. So you have gold least electropositive, and you have potassium most electropositive in the electrochemical series. So any of these components here, if you have hydrogen in a particular component, or let me say in a particular substance, it means that any of these components before this hydrogen, they are going to displace it. They are going to displace it. They are going to remove it away. But any of this one that you are having, lesser than it, they won't be able to displace hydrogen in its molecular form, like when it is together with another component in a compound. So, for example, copper can never displace hydrogen. Why? Because it's lesser than hydrogen in the electrochemical series. So, very important to note. Very important to note. So, let's take for example, you have CuSO4 copper 2 tetrasulfate 6 combining with zinc. So here, zinc, will zinc be able to displace copper? Let's look at it. Look at the position of zinc here. Zinc is here. Can we hear me?
Yes, sir.
Okay. Look at the position of zinc here. Zinc is up here. And then look at the position of copper here. So copper is lower. Although we can't arrange it straight. So just take it as this straight something. So zinc is upper here, like it's before copper. So it means that it is in the higher position in the electrochemical series than copper. So it's going to displace copper from the solution of this copper 2 tetrasulfate 6. So you're going to have displacement of copper away from here so that you can then have zinc 2 tetrasulfate 6 or zinc tetrasulfate 6, ZnSO4, and then the displaced copper come to stay here. So this is a single displacement reaction, okay? And this is the balance equation for that. This is the chemical equation for a single displacement reaction. So when you have MgCl2 plus zinc, what do you expect? you expect no reaction. No reaction. Why? Because zinc is not possible for zinc to displace magnesium, because magnesium itself is more electropositive than zinc. So when you now come to write the equation like this and then you write ZnCl2 plus Mg, know that you've written a very wrong equation. First, you must consider the electrochemical series. Can it displace this? Is it more electropositive than this? Is it more electropositive than that thing it wants to displace? So if so, yes, you can write the equation. If not, no reaction. Still on okay, single substitution. We talked about that. However, this place the C is a non-metal. So C is a non-metal. Here the C is able to displace A from here to have AC, and then the B standing alone, whereby C is a non-metal. So that is possible only if C is greater than B. That is, C is greater than B in what component? That is in non-metallic activity. The previous one we discussed was about metallic activity. That's electropositive activities. That's for metal. However, for this one, that's talking about non-metals. So it's talking about the ability to gain electron, ability to gain that. So that's about electronegativity now. So let's quickly look at very good example. So talking about the halogens, it is expected or should be noted that fluorine is more electronegative than chlorine, more electronegative than bromine, and more electronegative than iodine. So iodine is the least electronegative, and then fluorine was the electronegative element. So let's take for example, you have sodium iodide combining with chlorine. Yes, chlorine is more electronegative than iodine, so you expect it to displace it from there so that it can combine with that sodium so that you can have any cell and then you have your iodine hanging freely there. Also, you have sodium bromide combining with iodine. Where you see something like this, also you have no reaction. It's very similar to um, that metallic substitution. So single substitution as well. I think we've talked about this. So it's a metal, so we'll be able to displace H from there. Now we are looking at examples. So here we have hydrogen. Zinc will be able to displace hydrogen there because yes, it is more electropositive. So you have your ZnCl2, which is the salt, and then evolution of the gas hydrogen. Evolution of the gas hydrogen. So you have this reaction. Now you could also have double replacement. So in this kind of reaction, do know that there is a total exchange of ions. There is exchange of ions basically. We have AB plus CD combining together. There is this one come to displace this C and then combine with D to give AD. And then the C that is being displaced come to combine with B to form CB. So here just expect that they just exchange families. This one take this, combine with this one, and this one go to combine with the other one. So we're going to look at examples. So here you have sodium sulfide combining with hydrogen bromide. So this sodium goes to combine with the bromine, and then the hydrogen goes to combine with the sulfur. So hydrogen sulfide, yes. Hydrogen sulfide is not HSO. Hydrogen sulfide is H2S. So which means that you must understand your ion bearer, your valency, how valency have been interchanged, how valency has been changed, and how we result to the formation of the chemical formula. So chemical formula for hydrogen sulfide is HS, while sulfur is H2 minus. Hydrogen is H plus. Valency of H plus is 1. Valency of S2 minus is 2. So when they interchange, 2 goes to hydrogen, 1 goes to sulfur. So that's why you have H2S. Sodium bromide as well. So I believe you should be able to balance this equation. Also, this is also a double replacement equation. So if you don't call it double replacement, you call it a double decomposition. Actually, not all double replacement are double decomposition reactions. In a double decomposition reaction, you must have two soluble salts, soluble. They proceed to form product, one of which is soluble and the other is a precipitate, solid, not soluble. So you should know that not all double replacement reactions are double decomposition. Okay, not all double replacement reactions are double decomposition, but all double decomposition reactions are double replacement because yes, they involve exchange of ions. All double decomposition reactions involve exchange of ions. So here now you have potassium iodide combining with potassium iodide combining with lead 2 triazonitrate 5. So when that happens, this potassium here comes to displace this lead away from here. When it displaces lead, it leads to the formation of this potassium nitrite, KNO3. And then the lead that is being displaced comes to combine with lead, when it comes to combine with iodine rather, to form PbI2, lead 2 iodide. And that is the precipitate you see there. So you are going to have a down arrow here, a down arrow. So all of these equations, someone should take screenshot and you should try to balance the equation one after the other. So here as well, HCl combining with sodium hydroxide. So this is a reaction between an acid and a base now. So you do expect this sodium to come to displace this hydrogen here so that we can have NaCl as you've seen here. And then the hydrogen that's been displaced combined with the hydroxyl there to form H2O. So this is supposed to be H2O. So you can see it's a double replacement equation, but of course it's not a double decomposition. Why? The two components that are formed there are soluble. Water is actually either liquid, gas, or solid. But whichever, it is not considered a precipitate. And this one is soluble, water soluble. So the double replacement is not a double decomposition. However, the second on this line is the decomposition, double decomposition. So there are ways of balancing chemical equations. So someone should screenshot these equations and try to balance it. If you've done so, please let me know. Have you done so?
I've done that.
Okay, thank you. Now, balancing chemical equations, there are ways of balancing chemical equations which you should be familiar with. Uh, okay, so what are the methods? Inspection method, inspect, and also change in oxidation state or number method. So let's see how that is possible. So inspection. So you write chemical, of course, you've written down the correct symbols and correct formulas of the substances that are involved in the reaction. And then as the equation is being balanced, do not change the formulas and symbols. So hydrogen sulfide is H2S, it doesn't change. What you can only do is to add a number at the back at the front, like before the H. So like 2H2S, 3H2S, something like that. So you can't go and add a number to the sulfur. You can't write H2S2. No. You can't write H2S3. No. You can only write it before. So that is what this statement is talking about. As the equation is being balanced, do not change the formulas and symbols. 3. It is best to start balancing a formula unit which contain the highest number of atoms of an element, and these atoms should not be H and also should not be O. Well, maybe we are going to understand some of these statements while we progress. And if a radical is present and remain together, balance it as one entity. Also very important. And next to balance is H followed by O. Okay, so let's look at this one for example. A very good example. So here you have sodium hydroxide combining with hydrogen phosphate. So the hydrogen phosphate you have here, that's trihydrogen phosphate. Okay. Okay, so you have formation of this sodium phosphate, and then you have water also present there. So this one, who can tell me? Who can tell me the IUPAC name for this H3PO4? Anybody? Hmm? Who can tell me the IUPAC name? Is anybody on that? H3PO4. Who is doing that? I'm not sure if some people are actually present on this session.
Sir, the hydrogen,
You said what, Ashrafa? What's the IUPAC name of
the
H3PO?
hydrogen phosphate 3 acid,
What do you say?
the hydrogen phosphate 3 acid.
But you're having three hydrogen here. Oh, the meeting is about to end. Let me see. That's 15 minutes to the end of the call. Okay.
Oh, sorry, trihydrogen phosphate 3 acid.
Okay. Any other answer? Any other answer? So we come to mention, or we come to note the number of atoms that are present here. That is step one. Oh, sorry. You come to know the number of hydrogen atoms that are present, and that is step one. And then once you've identified that, you go over to the number of oxygen you have in here. That is step two. Before you then come over to, sorry, before you then come over to the phosphate that you are having here, which is going to be your step three. Does it make sense? Do we get what I'm trying to say? Can we hear me?
Yes, sir.
So to name this guy now, you go with the step one, which is this one. You identify the number of hydrogen atoms you have here, and then you go with the hydrogen there. Step two, you come to this last element here, which is oxygen. You also indicate the number. And then step three, you go over to the one at the center, the element or the atom at the center, which is phosphorus. Just to go there as well. However, to go to step three, you need to have, you must have calculated the oxidation number of phosphorus here. And to calculate the oxidation number of phosphorus, remember you need to remember your oxidation number rule, or rule of oxidation number. So 3 into brackets oxidation number for hydrogen plus oxidation number for phosphorus plus 4 times oxidation number of oxygen. I don't just want to write all there so that you won't get confused. Equals 0. Now, writing each of the oxidation numbers. For hydrogen, that is 1 plus phosphorus plus for oxygen, that is 4 into brackets negative 2 equals 0. So that you can have that P plus 3 minus 8 equals 0. And then at the end of the day, you have P equals 5. Have it together.
Yes, sir.
Yes, sir.
So if I want to name that compound now, I said step 1, you are going to indicate the number of hydrogen you have there. So which means I will say try hydrogen. That's try hydrogen. Step 2, you go to the bar. Indicate the number of oxygen you have there. Tetra, but it becomes oxo. Tetra oxo. And then you go to the last one, which is the third one, that's phosphate. Phosphate. And then you end it with what? With the Roman numeral of the number, oxidation number of the phosphorus that you calculated for. So that would be phosphate 5 in Roman numeral. So the name of that guy is trihydrogen tetraoxophosphate tetraoxophosphate 5 acid. Trihydrogen tetraoxophosphate 5 acid. Is it clear? How many minutes to
Yes.
Yes, sir.
the end of that? Okay, call where to. So I'm going to disconnect now. Let's join again once I send the link, okay? We will soon end the session.